Swayam Prabha. Digital India. Educated India.
Yeah, so again, let me have your attention. So you see, we have seen the so-called isoperimetric inequality, okay, and we next want to move on to the other important global theorem, which is the so-called four-vertex theorem, okay. So let's get into that. So um, you know the four-vertex theorem. So this theorem has a it has a nearly 100-year history, okay, and so the starting point was the result by an Indian mathematician by the name of Syamadas Mukhopadhyay, okay, and then you see this was he proved it for you know convex curves, okay, and then you see the proof was given for general curves, okay, and then there is also a converse. The converse was first proved for positive curvature throughout several decades later, and then finally it took almost 100 years for the full converse to be proved. So this result has a 100-year history, okay, but it was initiated by an Indian mathematician, okay. So what is the four-vertex theorem? So you take any simple closed regular and of course smooth plane curve, okay, then it must have at least 4 vertices, okay. And what are the vertices? Vertices are the points where the curvature has a critical point, okay. Vertices are points on the curve where the curvature, where the sine curvature has a critical curve point. So what you can imagine is that as the as you move on the curve is a it's a closed curve. That means it starts from some point and comes back to that point. So it's a closed curve, and it is of course simple curve. So it does not self-intersect, all right, and it is of course a regular smooth curve, okay. So that I can talk about curvature, all right. And then so you see, normally if you want to talk about curvature, you need the second derivative, okay. So the curve must be second continuously differentiable, okay. And we have this policy that whenever we look at some derivative, it should always be continuous, okay. So if you want you want to make sense of curvature of a curve, first of all the velocity vector should never vanish, that is, it has to be regular. Then the curvature vector is at least this magnitude of the curvature is given by the second derivative, magnitude of the second derivative, okay. If you take a unit speed parametrization, that is arc length parametrization of the curve, okay. So you need the curve to be C2 at least, okay. If the curve is C2, then the curvature is continuous, all right. But I want to talk about critical points of the curvature, So that means that I would like to have the curvature also differentiable, and then it should be differentiably continuous. So the curve must be C3. Okay, so the curve must be 3 times continuously differentiable, so that the curvature is 1 time continuously differentiable. And then I want to look at the points where the curvature has critical points. Okay, so where the curvature has critical points could in general be, they could be points of maximum, points of minimum, or they could be points of inflection. So essentially you will have maximum or minimum curvatures at vertices, or at a certain vertex it may happen that there is an inflection point for the curvature. Okay, the statement is that if you take a simple closed regular curve, and of course the smooth, I would like this to be C3. Okay, for reasons I explained, then it has at least 4 vertices. In fact, the fact is that it will have at least 2 local maxima and 2 local minima. Okay, so I will write that in fact the curve, in fact such a curve will have at least 2 local maxima and 2 local minima. Okay, so this is going to happen, and see this is a stronger statement, because you are saying that there are going to be at least 4 vertices which are actually local maximum minimum. Okay, and so you see now the of all these things, the fact that the curve is simple is very, very important, and a standard counter example is given by the limacon. Okay, so let me tell you about this counter example. So you see you have counter example is the limacon, which is given by r is equal to a into 1 plus 2 cos theta, okay, in polar form. And there is a little bit of a confusion here when you write it like this, which I will explain. So you see you have, so if you draw this curve, you see this curve is going to be like this, okay, and so you see this point will correspond to 3a comma 0, okay, and this point will correspond to of course theta equal to 0 and 2 pi, right. Then you will have I think let me draw it a little bit better the following way. So if this is 3a, then I divide it into 3 parts, then this is a comma 0, this point, and I'll take the same a here, so this will be 0 comma minus a, and I'll take this point here, which is 0 comma plus a. So these lengths are all a, okay, and this total length is 3a, okay, and the curve essentially the curve is like this. It has a outer loop like this, it goes like this, and then this is how this curve looks like, all right. And so this point corresponds to theta equal to pi by 2, okay, and this point corresponds to theta equal to 3 pi by 2. And the important thing is, of course, this is the origin here, and you see if you draw the tangent to the curve at the origin, you will get this angle, which will be 2 pi by 3, okay, and if you draw the tangent here, I will get an angle which is going to be 4 pi by 3, and the issue is that if you put for example any value of theta here, okay, then the only way I get r equal to a is by putting theta equal to pi by 2, okay. That will correspond to, you know, these 2 points, all right. Now to get this point inside, okay, that should ideally correspond to an angle of 180 degrees, okay. But the thing is that what you have to do is that if you put theta equal to pi, you are going to get r equal to minus a, okay. And then the point is that r is the you know, distance from the origin. That should not be negative. So the only way this should be interpreted is that, you know, it is, you have to write the x and y coordinates, okay. So x is, you know, your x is r cos theta, so it's going to be a into 1 plus 2 cos theta into cos theta, and y is r sin theta, which is a into 1 plus 2 cos theta into sin theta, okay. And now if you plug in the values, you know, values from 2 pi by 3 to 4 pi by 3 in here, what you will get is, you will get the inner loop, okay. So therefore, you know, there is some ambiguity when you write it like this. The inner loop you will not get it directly, you have to write the x and y coordinates, then you will get the inner loop, okay. So but so that is one point that you have to be careful about when you are looking at this equation, which is how it is usually written everywhere, okay. You have to be wary about the inner loop, the way it's the way it comes by only looking at the x and y coordinates, okay. You won't get it from this equation directly, right. Then the other thing is that, you know, the if you look at this curve, obviously, you know, if you take the if you calculate the dx by d theta and dy by d theta, okay, that is going to be the velocity vector, okay, and you will see that that will never vanish. Therefore, you know, it will be a regular curve, okay. So dx by d theta comma dy by d theta, you see, which is the velocity vector, this is never 0 0. Therefore this implies that, you know, this is the curve is actually regular, it's a regular curve, okay. But the issue is that, you know, in spite of it being a regular curve, it is not smooth here. At the origin there is a topological singularity, in the sense that, you know, there is a self crossing, so that's because it's not simple, okay. But the nice thing about this curve is that it manages to be a closed curve, it manages to be a closed curve which is regular, and it is it is not smooth, it is not simple, okay. Topologically it is not smooth at the origin, okay. Uh, but still it manages to have only 2 vertices. So you see that if I you know, if you take for example, you know, at this point a comma 0, here you will have the smallest circle of curvature, okay, and here you will get the minimum radius of curvature, so you will get the maximum curvature. And if you go here, then, you know, you get a bigger circle, okay. And so let me not so I will get a bigger circle here, all right. And therefore you have, at this point I will have, you know, minimum radius of curvature, so I will have max curvature, and here I will have, at this point I will have minimum curvature, and you have only 2 vertices, okay. So it's a counter example that, you know, if simplicity is very very important. If you don't have if you relax simplicity, then you are going to have a possibility where you can have exactly 2 vertices, okay. But if you put in simplicity, then you know, you will get also smoothness, and on top of that you will get at least 4 vertices. In fact, you will get actually 2 local maxima and 2 local minima, okay. So the exact case where you get exactly 4 vertices is the case of the ellipse, okay. If you take an ellipse, for example, okay, then as you can see, at the with the major axis, at the 2 ends of the major axis, you will get, you know, the minimum curvature, I mean you will get the minimum radius of curvature, so maximum curvature. And at the edges of the minor axis, you will get maximum radius of curvature, so you will get minimum curvature. So you get 2 points which are local maxima and 2 points which are local minima, so you get 4 of them. That's the minimum possible, okay. So that is a statement, and here is a counter example. So the simplicity is very very important, okay. And so the way we prove it is we prove it for the easily accessible case, which is the convex case, okay. And if possible, I will try to indicate what happens in the non-convex situation, okay. But the point is, the proof in the convex case, which was the first case that was proved, you see, it interestingly involves clever use of the Front-Esseré relations, okay. So and you can expect that, because you see the sign curvature is involved in the statement, okay. So let me so let's go ahead. I'll just say proof, we shall uh, consider the case when the curve is convex, okay. So this convexity of a curve is something that can be stated in many ways, okay. And see, since this is a simple closed curve, you see it's a Jordan curve. Therefore, the Jordan curve theorem applies. So the interior of the curve makes sense, okay. And convexity can be stated variously in using the interior also. So I'll just make I'll make a lemma here, which is kind of very easy, and you can uh, uh, you can verify it. So for a simple closed curve, simple closed continuous, that is Jordan curve, the following are equivalent. And of course, whenever I say curve, I am only worried about plane curves, all right. The following are equivalent and define convexity of the curve, okay. So the first thing is, you see, you take any 2 points on the curve, okay, and then join them by a straight line segment. Then every point on that line segment should either be on the curve or in the interior, okay. For any 2 points on the curve, the straight line segment joining them is I want to say that for any 2 points on the curve, if you take the straight line segment joining those 2 points, every point on that straight line segment is either in the interior of the curve or it is on the curve itself, okay. So let me say this, for any 2 points on the curve, every point on the straight line segment joining them is either on the curve or in its interior, okay. Now you see so this is one characterization, okay. Then so the way we see it is, suppose suppose I have something that's like this, let us say, okay. Then the problem is that you can see that if I take 2 points like this and join it, you see I am going to get points outside, okay. And therefore this is not convex, all right. So whenever the portion of the curve caves in and caves out, then obviously it's not convex, all right. And of course it may happen that the curve 2 points on the curve, when you join the line segment, that may belong to the curve itself, because the curve itself may contain a line segment, okay. So the other possibility is that you can also have something like this. So you just think of something like a triangle, okay, and then I just take the three sides, and I join them by nice arcs, okay, like this, okay. Then this is also convex, And the thing is that if you take this point and you take this point, the line segment joining the point, these 2 points is completely on the curve itself. There is no point inside. Okay, that is also allowed. Okay, so this is not convex, and this is convex. Okay, and the condition is that this is the condition that is based on the line segment joining 2 points on the curve. Okay, now there is also and very important thing is that there is to make sense of this condition, you need the interior of a curve, and that interior is guaranteed by the Jordan curve theorem. So that is the important thing. Okay, the Jordan curve theorem is without the Jordan curve theorem, you cannot make sure that an interior exists. Okay, so that is used. And the next characterization is, you take since you know that an interior exists, take any 2 points in the interior and join them by a line segment. Okay, then that line segment should contain entirely, it should consist of points which are in the interior. That is also convexity. Okay, so I'll write the second one for any 2 points on the curve, for any 2 points in the interior of the curve, incidentally which exists because of Jordan curve theorem. Okay, the line segment joining them lies entirely in the interior. Okay, so for example, again this in this situation, if I take the tangent line here, okay, and join these 2 points, then you see this is in the interior, and this is also in the interior. But of course this point is on the curve itself, so it's on not in the interior. So you see the convexity is violated. All right, then the third condition is that you can also say this in terms of tangents to the curve. You take any tangent to the curve will always lie on one side of the tangent. Okay, any line in the plane divides the plane into 2 half spaces. Okay, and if you give me an orientation for the line, then I have the right side and the left side. So I have a right half space and I have a left half space. And so if you take any tangent line to the curve will lie in exactly 1 half space. Okay, so that is also convexity. The curve lies on one side of each of its tangents, lies on only one side of each of its tangents. Okay, so at a point where the curve caves in, I can draw a tangent, so portions of the curve will stretch on both sides. Okay, so that is also convexity. And then there is one more way of describing convexity, which is if a line hits the curve exactly at 2 points, it will divide the curve exactly into 2 pieces. Okay, so that is also another way of saying it. If a straight line cuts the curve at 2 distinct points, then it cuts the curve into exactly 2 segments or pieces. So all these four are geometric ways of describing convexity, right? And you can check that they are all equivalent with some work, okay? But the one that we want to use is this one, namely that if a straight line cuts the curve at two distinct points, and I should say at exactly okay, two distinct points, okay, then it will break the curve down into two pieces, all right. I want to use this characterization, all right. So what we will do is, so this is just a lemma, and it's kind of geometric lemma which is pictorially, geometrically it is evident, but then you can try to prove the the equivalences of all the four conditions, okay. Now what we will do is that we so you see so we have the following situation. We have a curve, it is simple closed, it is convex. Now we have assumed it's convex, and it is smooth, and it's also regular, okay. Now what I have to show is that there are at least four vertices, okay. So that means if I want to say that this is possibly wrong, okay, assume that this is wrong, the statement is wrong, then I should be able to find curves like this which have less than four vertices. So it may have one vertex or two vertices or three vertices, okay. And what I am going to do is that I am going to assume that there is such a curve, and I am going to get a contradiction, okay. And this is going to be just a very clever use of the Frobenius-Array relationship, okay, and some very simple integration, okay. So let me say the following thing. By the way, I have to rule out two cases. See, if the curve, you see if the curve contains a portion of the curve contains an arc of a straight line, then along that arc, you see, the curvature function is 0 actually. Therefore, its derivative is also 0 there, identically. That means every point on that arc, on that straight line segment, which is contained in the curve, at every one of those points, you see, you are going to get a critical point, and there are infinitely many of them, okay. And this is not a case we want to consider, because we are worried about minimum number of vertices, okay. So I am going to assume without loss of generality that the curve does not contain any portion of a straight line, okay. Then similarly, I will also assume that the curve also does not contain any portion of a arc of a circle, because there also it is the same situation. On a circle, you see, the curvature is constant, so the derivative is 0 throughout. Therefore, all the points are critical points, and there are infinitely many of them. So I am going to look at a curve where no portion of the curve is is an open arc from a straight line or a circle, all right. And what does that mean? It means that I cannot have a situation where the sine curvature is constant. In particular, the if you look at the derivative of sine curvature, okay, then except for there is not going to be any portion of the curve where the derivative of sine curvature is identically going to vanish, okay. Because if on a portion of a curve okay, a curve is, say, defined on an interval, which where a closed interval which is the parameter space, okay. If on a subinterval, the curvature the curvature, I want to say that the curvature will never be identically 0 on any subinterval. Rather the it will never be identically constant on any subinterval. Okay. On a subinterval, if the sine curvature is going to be constant, okay, then its derivative is going to be 0, and on that subinterval it should be either an arc of a straight line or an arc of a circle, which I don't want to assume. Therefore, I just want to say that the curvature function is, if you take the derivative of the curvature function, that is not going to vanish on any subinterval. That's what I want. Okay, so let me write this down. We assume given a curve gamma equal to gamma of s. So I'll use the arc length parametrization, because eventually I want to use the Frone-Seray relations, and for that I need the arc length parametrization. Okay, so gamma is from let me put 0 to L of gamma 2 R2. S is the arc length measured, say, from gamma of 0, let us say, and with, of course, it's a simple closed curve, so gamma 0 is gamma of L of gamma. Okay, so it's a closed curve. Okay, and gamma, rather its image, is actually convex, and gamma is simple. So this means that gamma restricted to, let me remove one of the endpoints, say the starting point, this is injective. Okay, so it is a simple curve, and you also assume that and gamma does not contain any portion of an arc of a straight line or of a circle. Okay, because in these two so-called degenerate cases, there are infinitely many vertices. Okay, so you see, you have thus if you take the sine curvature of gamma and you take its derivative, that is never going to identically vanish on any subinterval. Okay, thus is never going to vanish on any subinterval of 0 L gamma. Okay, so this is not going to happen. So I should say, maybe I should say the derivative. Yeah, so what I mean is derivatives. Thus the so there is a dot here. Okay, so thus the derivative of the sine curvature of gamma is never going to vanish on any subinterval. Of course, what this uses is the fact that if it does so, then on that subinterval, the curvature, sine curvature is constant, and that means on that subinterval, the arc must be, either a portion of a straight line or of a circle. This is something that we have already proved. Okay, so you are not assuming that. Okay, for on a straight line or a portion of a straight line, every point is a vertex, and there are infinitely many of them. And similarly, on a circle or any portion of a circle, every point is a vertex, there are infinitely many of them. So we are not bothered about those cases. All right. Now, so what we will do is that we will show that there is no situation where you have less than 4 vertices. Okay, we show that there cannot be a situation, a curve gamma, of course satisfying the above, which has either 0, 1, 2 or 3 vertices. Okay, so you have to contradict all the cases, right? Now as we will see, the only case that is going to boil down to is the case of 2 vertices. Okay, so so you see this gamma is C3. So this means that Ks gamma, so Ks dot gamma, so Ks gamma is actually C2. So I want to say it is C1. Okay, Ks gamma is just is C1. Okay, and the Ks dot gamma is actually is C0, which is continuous. Okay, so C3 is thrice continuously differentiable, and the curvature is first continuously differentiable, its derivative is continuous. Okay, now you see, so you see, look at the curve is from 0 L gamma closed interval into R2. If you take the sine curvature of gamma, that is going to be from 0 L gamma into R. Okay, it's a, so it's a, the sine curvature is a real number with the sine. Okay, and you see this is of course continuous, because you see the so you so I want to actually worry about yeah, so that's right. Yeah, so I want to look at the sine curvature. Sine curvature is continuous. In fact, it's actually C1. Okay, so you see now there is a little bit of topology that comes into the picture, and the topology is that you see if you take a real valued function on a closed finite bounded interval, okay, then the image of that is also a closed finite bounded interval. Okay, so there is a little bit of topology that is involved here. So fact from topology, or if you want to call it as analysis, is that Ks gamma, the image of this 0, this whole closed interval, is going to be so I will write it as small m comma capital M on the real line. Okay, so that means that this small m will be the minimum of the sine curvatures, and this capital M is going to be the maximum sine curvature. So you see, so this is a rather a deep fact, that a continuous function on a closed bounded interval will attain a global maximum and a global minimum. Okay, and the reason for this is the following. It is what is called as compactness in topology. If you take any subset of the real line, okay, which is what is called as compact, the condition is that it has to be closed and bounded. Okay, and it will break down into a finite disjoint union of closed intervals. Okay, and that is one important thing. In particular, if you take a closed and bounded interval, it is compact. This is part of what is called as the Heine-Borel theorem. The Heine-Borel theorem says that a subset of Euclidean space is compact if and only if it is both closed and bounded. Okay, and the beauty of this compactness is that when you take a compact set and take its image by a continuous function, the image is also compact. Okay, so as I had said earlier, see, if you take a closed set and you take the image under a continuous function, the image need not be closed. Okay, if you take a bounded set and take its image under a continuous function, the image may not be bounded. But if you take a closed and bounded subset together and take its image, the image will be both closed and bounded. This closeness and boundedness put together give compactness, and that's a very deep thing. Okay, and that this closed and boundedness give compactness is exactly the Heine-Borel theorem. So the point is that if you don't want to worry about these topological things, you just have to remember that if you have a continuous real valued function on a closed bounded interval, it will attain a maximum and it will attain a global minimum. You will have a global maximum and a global minimum. That is always true. Okay, and of course, you see, I need a closed and bounded interval. Why I need closed is that closeness is whether the endpoints are there. If I remove an endpoint, I can easily get into trouble. For example, I can just take open interval 0, closed 1, and I can take the function 1 by x. If you take the function 1 by x for x greater than 0, from open 0 to closed 1, okay, that 1 by x is of course continuous, but at 0 it's not bounded. In no neighborhood of 0 is the function bounded, because 1 by x goes to infinity as x goes to 0. So you see, therefore the function is not bounded. So you need closeness, and boundedness is also important, because if I could simply take f of x equal to x on the real line. Okay, the real line is an unbounded interval, and if you take f of x equal to x, the function is unbounded. Okay, so if the domain is either not closed or it is not bounded, then you see the image cannot be bounded. Okay, but the beautiful thing is, if you have a domain which is both closed and bounded, then the image is also going to be closed and bounded. And the other important thing is that there's also this topological business of connectedness. See, this interval is connected. Okay, in fact, it is a topological fact that any subset of the real line is connected if and only if it is an interval. It doesn't matter whether the interval is open or closed or half open or half closed. The only connected subsets of the real line are intervals. And the beauty about connected sets is that when you take a connected set and you take its image under a continuous map, the image is also connected. Okay, so what is going to happen topologically is that this closed bounded interval, it's compact, so its image is going to be a finite union of closed bounded intervals, which are disjoint union in general, but it will be finite because of compactness. And then because this interval is also connected and the image of a connected set is connected, the image of this interval will also be an interval. Therefore, the moral of the story is, putting both together, the image of a closed interval has to be a closed interval again, which is bounded. And the small m and capital M are the endpoints of that interval. The small m will be the minimum and capital M will be the maximum. So, moral of the story is, from topology itself, if you want, okay, the sign curvature certainly has one global maximum and one global minimum. Okay, and by definition, these are two vertices already available. Okay, so therefore, you will not get the case where you have 0 or 1 vertex. That will never happen. You have at least 2. You have at least 2 vertices. Okay, so the fact that there at least 2 vertices are there is guaranteed from topology. Okay, now you have to only worry about one situation where two situations rather, that there are exactly 2 vertices. If there are exactly 2 vertices, they have to be these 2 at the points where the sign curvature are having a global maximum and a global minimum. Okay, then the other thing is, there may be one more extra vertex. That one more extra vertex, if you think about it, it can be of 2 types. Either it is again a local maximum or a minimum, or it may be an inflection, okay, point, which is neither a local maximum or a minimum. But what you must understand is that if it were again a local maximum or a minimum, okay, then you will have two local maxima or two local minima consecutively on the curve, and therefore between any two extrema of the same kind, there will be one more extremum of the opposite kind and you will get four vertices. Therefore, the case that you have to worry about is when you have three vertices and the third vertex is actually a point of inflection. So these are the two cases you have to worry about. Either there are exactly two vertices which are points where the sign curvature has global maximum and global minimum, which is always there, it's guaranteed by topology, okay, or there is one more vertex and that vertex is neither a point of local maximum or nor a point of local minimum, but it's a point of inflection, okay. But so here is the key point. So in either of these three, in either of these two cases, if you take these, there are 2 points on the curve, okay, so that if you take the line joining those 2 points, that will break the curve into 2 pieces, because that is where convexity is there. And on these 2 pieces, here is the important thing: the curvature signs, the signs of the the derivative of the curvature, they will be the same. So let me explain that. So that is the critical part that has to be observed. Okay, that is critical to the proof. So you see, so let me write this. What example are you thinking about? But certainly it is not in this case. Yeah. In this case, there is no issue. You understand that? Yeah. So of course there is a little bit of confusion in the sense that you can either take a point on the curve and look at its curvature. So as I understand what you are trying to say is that when you are looking at the curvature function, physically you can look at it at a point on the curve. So it looks like the domain is the points on the curve themselves. Okay. Now, or if you want to look at the domain as this domain of the parametrization, okay, there is a seeming difference between these two, except that because this is a closed curve, at 0 and L of gamma, all the functions that you worry about on the curve, they are the same. So normally what we do is that you can either look at all functions as being defined on closed interval 0 to L gamma with at the boundary, the values are the same, okay. And for example, if you want such a function to be, let us say, n times differentiable, that means at the left hand point, you should have n times differentiable from the right, and from the right hand point you should have n times differentiable from the left, and then all the derivatives, two-sided, all the one-sided derivatives, corresponding derivatives, they should agree, okay. So it is understood in that sense. So you can view it in either way. If you view it as on the curve is compact, that is also true, okay. If you view it as a function on the parameters space, which is the closed interval, that is also compact, there is going to be no issue, okay. So it will not create any confusion, all right. You have to only remember that at the distinct points on the curve correspond to distinct parameter values, except for these endpoints of the parameter space of the interval, which correspond to only one point on the curve, where you assume the curve starts and ends, okay. But what was your question? See, the curvature is see at the ends you will have cusps, right? Yeah, the curvature is a continuous function because at the wait, you are taking not the curvature of the ellipse. You are taking curvature of the asteroid. If you take curvature of the asteroid at the cusps, it will go to infinity, right? It's not regular. It's not regular. Yeah. yeah. But I need a function which is which is real valued, no? So at those 4 points, it will take whatever plus infinity or minus infinity, whatever you want to say it. Actually, it will flip, right? Because in one direction you will get plus infinity, and the other direction it will become minus infinity. It's a Is that so? Uh, okay. Uh, oh, it's not like the cycloid. Okay, yeah, all right. Yeah, but the point is, this is so. Then the problem is that your function is not defined at those 4 points. That is a problem. That's a problem. Okay. There is a way of doing this in topology. What you can do is that you can take the real line and you can put one point on the right as plus infinity and one point on the left as minus infinity, and this is what is called a 2-point compactification. You can do that. You can add plus infinity to the right and you can add minus infinity to the left, and you can make this 2-point compactification. This is called the extended real line. It's compact now. And now if you allow the plus or minus infinity values, this will become everything will be fine. If you include plus or minus infinity, you are in good shape. Because you are allowing these as actual values. Then it is okay. Otherwise, what you said is very right. If you take the asymmetrical asteroid, or for that matter any asteroid, then at those points, the curvature goes to infinity. Okay, because actually the radius of curvature the circle of curvature will just become reduced to a point. Therefore, the radius of curvature goes to 0. Its reciprocal, which is the curvature, will go to infinity. So at those 4 points, no real value is defined. So you are going to get, so if you take it as a function into R, then at those 4 points is not defined. So then it is like, not compact. But if you want to define at those 4 points, you have to take it into the extended real line, which is actually compact. Okay, and then this is a 2-point compactification. You can make it 1 point by making it a circle. That is also possible. Then you have to take the magnitude of the curvature, right? So yeah, so that's a good thing to think about.